Okay, good morning all of you. Let's get started. Any questions on what we covered so far? Please note that you need to take a note, not just simply watching the video, okay? It is not going to help you much. So you please follow my suggestion. So this is what we covered yesterday. After getting governing differential equation for beam, we adopted variational approach and try to get the potential energy functional, and we noted this potential energy functional for two cases: when essential boundary conditions are specified at both ends, and when essential boundary conditions are specified at or not specified, or sorry, one is essential boundary condition being specified at both ends. Second one is natural boundary condition being specified at both ends. So for both cases, we derived potential energy functional, and also we derived the element two node beam element shape functions. So this is the potential energy functional. This is the differential equation. This is the starting point. Differential equation multiplied with variation of the quantity that you are trying to approximate, integrated over the problem domain. All these integration by parts, all this needy greedy stuff. Finally, if essential boundary conditions are specified at both ends, this is the potential energy functional. And if natural boundary condition is specified at both ends, this is the potential energy functional. And I told you, you don't need to go through this procedure if you are comfortable with structural mechanics concepts. And if you are strong in it, you can directly write this potential energy functional. It is nothing but strain energy minus work done with applied forces. Once you get the potential energy functional, you need to make a substitution of finite element approximation of V and derivatives of V. For that, we need to pick or decide on the finite element shape for what kind of element we want to use. Here, shape functions for two node beam element are derived. Yesterday I told you about all this derivation. So once we get the finite element shape functions, we can write this approximation of V transverse displacement over an element like this N transpose D. So V is nothing but a row vector comprising of shape functions multiplied by a column vector comprising of the nodal values. This is row vector comprising of shape functions, column vector comprising of nodal values, N transpose D. And in our finite element or this potential energy functional, we also have derivative of V, second derivative of V with respect to X. Second derivative of V with respect to X. So that also we need to make a note before we go and substitute it to the potential energy functional. So this is V in terms of S. If you want derivative of V with respect to X, you can make use of chain rule and write like this. This is where we stopped yesterday. The plot of the finite element shape functions for two node beam element. So let's continue from here in today's class. So please make a note of this one. First derivative of V with respect to X. This is nothing but slope. It's nothing but slope, and you can make use of chain rule And also we know what is the ds over dx based on the mapping. So you can write this derivative of v with respect to x in this manner. And now you just have an approximation of v in terms of finite element shape functions and nodal values. So you can take derivative of it, and then this is what you get. Please take a note of this one. Please keep in mind here, these expressions for finite element shape functions are derivative expressions for finite element shape functions. They are valid only for that mapping. Here we mapped onto a parent domain going from 0 to 1. Instead of that, if you decide to go with a domain going from -1 to 1, then you need to rederive all this. Okay. But finally, your result is not going to have any effect provided you do properly. So this is first derivative of v with respect to x. So this is first derivative of v with respect to x. But in the potential energy functional, we have second derivative. So you need to take one more derivative of it. If you want one more derivative of it, you can actually either make use of chain rule, or you can start, or you can here. This you take derivative with respect to s and derivative of s with respect to x. So you can use one more time chain rule and get the second derivative of v. So you need to take derivative of all these quantities with respect to s once again and multiply with 1 over L. So you are going to, for second derivative of v with respect to x, you are going to get 1 over L square and derivative of all these quantities. These are nodal values. So they are going to be like constant. So this is what second derivative of v with respect to x looks like. And if you simplify, this is what you get. And this quantity, whatever is there here, this quantity 1 over L square and multiplied by whatever is there in the square bracket, that quantity is denoted with B transpose. And this is the nodal unknown vector, unknowns at the nodes, that vector, so that is denoted with D, B transpose D. In your potential energy functional, you have square of second derivative of v. Please note that what is second derivative of v with respect to x? It is nothing but curvature. Curvature is a scalar quantity. Curvature is a scalar quantity. If you take square of a scalar quantity, you can write it as that quantity transpose times that quantity. So we can, this kind of thing we did, or this kind of algebraic manipulation we did even for bar element. Similar thing you need to do here. And plug in all this information. Plug in all this information. Wherever v is there, replace with n transpose d. Wherever second derivative of v square of second derivative of v is there, you replace that d, b, d transpose b, b transpose d. And if you do all that, you get this equation. And anyway, for each of the terms, when you substitute these approximations, how it becomes, it is shown here. And one more thing, the limits of the integration are going from x1 to x2. x1 is mapped to s is equal to 0. x2 is mapped to s is equal to 1. So if you want to write in terms of parent domain, it's going to become 0 to, integral limits become 0 to 1. And wherever x is there, replace with L times ds. Wherever x is there, replace with L times ds. So please make a note of this one. So this is first term because of bending strain energy. And you can see here this quantity which is inside the integral, EI times BB transpose. Suppose if beam is flexural rigidity of beam is constant, then you can take EI out of the integral. And but unlike for a bar element, 2-node bar element, here please note that B is not a constant. B is function of S. B is function of S. So when you take B transpose, you are going to get some polynomial in terms of S here. So when you want to implement it in a computer code, this is where you need to use numerical integration. So limit going from 0 to 1, some polynomial is there, or what is the order of the polynomial, you can easily check. B is linear here. All the terms in B are linear. So when you take B transpose, you are going to get a quadratic. The polynomial is going to be quadratic. And when you are implementing in computer code, you can use numerical integration. Okay. Since it is quadratic, you can use even 2-point integration. Okay. And if EI are not constant, then you can put them inside the integral. Then that whatever is in this degree of that integrand is going to be maybe it may be something else instead of quadratic. Okay, so this is the first term. Similarly, in the second term, third term, all those terms you need to make the finite element approximation substitution wherever it is required. So now let's see the second term, which is associated with distributed load. Second term, which is associated with distributed load, it is x1 to x2 q times v dx. Limits have to be changed from 0 to 1. Q, it's going to be a function of x, or if it is not function of x, you can take out of the integral. V is n transpose d, and dx is L times ds. So substituting all those that information, finally you can define a vector. You can define a vector here. RQ is defined. RQ is going to be a vector. And if RQ is defined like this, then WQ can be written as D transpose RQ. And once this distributed load is over, whatever is left out are all concentrated forces and moments. So there is no finite element approximation required there. So you can directly write, or you can, since we are writing everything in terms of matrix and a vector or vector transpose vector kind of notation, this last the work done due to the concentrated forces and moments, that also you can write in terms of multiplication of vectors. D transpose or RF. RF is defined like this. So once you have all this information, you plug in into the potential energy functional, you get this one. And now once you get potential energy functional, you need to apply stationarity condition. So please take a note of this. If any questions are there, please let me know. No questions? Everything is clear? So finally, this is what you get. KD equal to some force vector. And here force vector is comprising of contribution from the distributed load and concentrated forces. And please note that whatever we derived this element equation system is a general one. Okay. And please note that when we derived the element equations for a bar element, once we got the element equations for a plane truss element, okay, plane truss element, and I told you that element equation is going to exactly match with whatever you learned from your structural analysis. So here also your approach is different. Finally, please note that an element is, let's say an element is there, a structural member is there, whether it's beam or bar. Forever, because we are developing several tools, we can use any of these tools or any of these approaches and try to approximate its stiffness. But that only single bar is there, and even if you use different approaches, even if you approach or you adopt different approaches, n number of approaches, finally, and all the n number of approaches should give the same stiffness or same element equations, because same quantity you are trying to describe using different approaches. Anyway, the point I want to make is this equation system, element equation system, should be in accordance with what you learned in your structural analysis. If it is not, then there is a problem either with whatever you learned in structural analysis or whatever you are learning here. So let's see that. Now here is written in a compact notation, KD equal to R cube plus RF. So now K we already noted in the previous slide, K is given by this, and B transpose can be obtained once B vector is defined. So we know what is K. It's a matter of doing this integration, and K is going to be of dimension. B transpose here is 1 row 4 columns. B is going to be 4 rows 1 column, and B transpose is 1 row 4 columns. So 4 by 1 multiplied by 1 by 4. So K is going to be 4 by 4 matrix. So let's try to find out that 4 by 4 matrix. At least please note that here EI is inside the integral. So assuming flexural rigidity is constant, let's try to find what is this K, how it looks like. Okay, this is how it looks like. You do that multiplication and do that integration, and finally this is the K matrix, stiffness matrix for beam element that you get. The stiffness matrix, this stiffness matrix is valid when EI is constant. If EI is not constant, you know what to do. You just take this inside the integral and then do the integration. Okay, but for specific case where EI is constant, this is how the stiffness matrix for a beam element looks like. So you go back to your structural analysis and check the stiffness matrix, whatever in your whichever textbook you followed. You see this stiffness matrix for a beam element. For a beam, what is the stiffness matrix? How it looks like from your structural analysis concepts. Okay, you might have used different approach to derive each of these components in your each of these components in stiffness matrix. When you are trying to get this kind of stiffness matrix in your structural analysis, but here the approach is different. Finally, the stiffness, whatever we get, it should match with whatever you get from structural analysis. So you please make a comparison, okay? And again, stiffness matrix is going to be symmetric. Stiffness matrix always going to be symmetric. Okay, stiffness matrix is always going to be symmetric unless as long as the structural system, obeys Betti's reciprocal theorem. Okay, as long as the particular structural system that you adopt or that you are looking at, if it obeys Betti's reciprocal theorem, then stiffness matrix should be symmetric. It's simple logic. What is the distance between the point where I am now staying and where you are staying? Is going to be same as the distance, my distance from you is going to be same as your distance from me. So same logic here. All the ijth terms are going to be same as jith term. In stiffness matrix, whichever component is there at I and j location, it's going to be same as the component in ji location. So this is stiffness matrix for beam element, two node. We adopted two node beam element. For that, stiffness matrix is given by this. And the rest of the quantities, RQ again involves integral, that is also simplified. And finally, element equation system for a beam element looks like this. You please take a note of it. I'm not seeing or I'm not hearing any of the comments or questions. I don't know whether everything is clear, or there are two ways or two situations where you can keep quiet. One is either everything is clear or everything is not clear. Okay. I hope it's the other way, everything is clear. If you have any questions, please let me know. This is the element equation system for an element which is subjected to distributed load along the length of the element, as well as moments and forces at the nodes. Okay? And if moments and forces, concentrated forces and moments are zero, this vector is going to be zero. Whichever is zero, that depends on if distributed load is not applied over that particular element, this vector is going to be zero. So please take a note of these element equations. And there is a figure down. There is a figure down here. What actually it is showing is these quantities, this vector QL divided by 2, QL square divided by 12, QL divided by 2 minus QL square divided by 12. These quantities are shown based on the sign conventions. Please note that this vector is on the right side. So it is going to be similar to the given the distributed load. What are the equivalent given the distributed load? What is the equivalent force at node 1? Equivalent moment at node 1? Equivalent force at node 2? Equivalent moment at node 2. Okay. And here, what we started out with, we are assuming Q is in the positive direction of y-axis. Q is acting in the upward direction. Okay, and this is a positive quantity here. Finally, when we did this integration, finally it turned out this is positive, this is positive, this is positive, this is negative. Okay, positive, negative, all this is all mathematics, understand? Finally, you try to show me physically how these moments and forces are going to act on a beam element. So that is what is depicted here. So an element, beam element is there. On that beam element, distributed load is acting. That distributed load, when we are assembling finite element equations, we are going to convert, or we are going to because of the distributed load, we are going to find what are the equivalent forces and moments at the nodes. So that is what this vector is. So now Q is acting in the upward direction. That is what is shown here in this figure. And Q is uniform. Here, please note that Q is taken out of the integral. So it is assumed Q is not function of X. Q is not function of spatial coordinate. Q is constant. That means Q is constant, uniform. That is what is shown in the figure. Q is acting in the upward direction. Q is constant. And what about this? Why it is shown like this? We are following the sign conventions. We are following the sign conventions. Sign conventions for what? Here the sign convention that is followed is, you just need to, that's why I told you in the beginning, you need to make a note of this sign convention. This is sign convention for nodal degree of freedom, applied forces and moments, and this is for internal moments and internal shear. Okay, internal forces, internal shear. So please take a note of this sign convention if you have not noted. Okay. Let's see this one. So I'm trying to give an explanation how this vector is related to this. And if you follow the sign convention, Q is QL divided by 2, positive. As per applied forces and moment, this should be acting in the upward direction. Okay, but here it is shown acting in the downward direction. We'll see why. And this is also based on the sign convention. All the forces acting in the upward direction are positive. So this also should be acting in the upward direction, but it's shown in the downward direction. We'll see in a while. Okay, this one. And here the sign convention is all the moments acting in the counterclockwise direction are positive. So this is positive, so it should act in the counterclockwise direction. But it is shown as in the clockwise direction. Again, we'll see why. And this one is negative. If it is negative as per the convention, it should be acting in the clockwise direction, whereas it is shown as though it is acting in the anti-clockwise direction. So here, this if you take a fixed beam, of same span of the length of that particular element that you are looking at, applied with uniformly distributed load, and try to, from your structural analysis background, if you try to find what are the going to be the reactions at this support, what are the support forces and support moments, or the reactions at the support which are going to be force and moment. If you try to find that for this kind of loading acting in the upward direction for this kind of loading, this is what you get from your structural analysis. If you forgotten, you just see that. And what is the relation between the quantities that are shown in this figure and this one? Magnitude wise, they are exactly matching except this sign. So what the inference from this is, this vector Q, or this which is having this distributed load vector, if you want, you can do this integration and get that. If you don't want to do this integration, this vector is going to be same as treating that particular beam element as though it is fixed, and based on your structural analysis background, you find the reactions at the supports and put those reactions at the supports with proper sign convention as per applied loads and moments, whatever sign convention we are following. Once you put it in a vector and reverse those signs, you first put these reactions based on the sign convention that we follow for applied forces and moments. Once you get that vector, you reverse the signs, then that is how you get this vector. So there is a relation between this and that. Okay. Anyway, this is an interpretation or some explanation how this vector is related to this. So instead of doing this integration, you can, if you are strong in structural mechanics, you can directly write this vector. That's what the message I want to convey. Any questions here? Please take some time, and if there are any questions, please let me know. Any questions? So now we are ready to solve some problems. We are ready to solve some beam problems. And please note that beams, you can have point loads, or you can have uniformly distributed loads, or you can have varying loads. Okay, where load variation can be any pattern. There is no restriction on that. But let's see some we derived this element equation for a two-node beam element, but we should also try to understand what is is this if I use this element equation, will I get exact solution for all kinds of problems, or is there any limitation on this? So I will quickly bring to your attention some important point, then we'll go ahead and solve the problems. Okay, and here the point or the important thing is you need to pay attention to here. Here, for the two-node beam element that we derived, V is N transpose D, and over an element, how this V is vary is going to depend on the degree of these shape functions, okay, or order of these shape functions. Here this is a cubic, this is cubic, N1, N2 are cubic, and N3, N4 also cubic. Okay, so V is going to be cubic, the variation is cubic. So that means if your displacement, if your transverse displacement over the element, is cubic, up to cubic, this two-node beam element should be able to capture. Okay. And what about this one? If your rotations, you can see here rotations are slow. The highest order of S is 2. So it is quadratic. So as long as your slope in that particular element is having up to quadratic variation, this element is going to capture exactly. It's going to capture exactly. Okay. Sorry. It's going to capture exactly. And what about second derivative curvature? Curvature, you can see it's linear. So this element is going to be able to capture if the curvature is linear over the element, up to linear. It can be constant or linear, it should be able to capture. But if curvature is quadratic, you will have some error if you are using this element. And what is the relationship between bending moment and curvature? Bending moment and curvature, EI times second derivative, square of second derivative of V with respect to X. So if you take square of this curvature, multiply with EI, it's going to be your bending moment. Okay. So bending moment, if it is if it is having higher order variation, then you may have problem in capturing that. So that you need to keep in mind. Anyway, you will have a better feel for it when you are solving a numerical example. So this two-node beam element, may not be able to give you exact results for all types of loads. Understand? It may be exact for few types of loads, and if it is the load variation is something else, this beam element may not be giving you exact result. Okay. So with that, anyway, I just gave you that information. Again, we'll come back to that point at a later stage. Now let's take an example where this element is going to give you exact result. So take a note of this element equation. So now let's take a simplest problem. Let's take a continuous beam having 3 spans subjected to a point load in the middle of midspan. Okay. So take a note of these element equations. This example. Before that, one more thing. This is element equations. Once you get element equations, you solve the element equations, get the nodal values. Once you get the nodal values, displacement at any point in the element can be interpolated using N transpose D. There is nothing but N transpose. This is a D. Okay. And bending moment at any point. Bending moment at any point is given by this one. Sorry, I think I made a mistake earlier. I mentioned bending moment, moment curvature. Just now I made a mistake. Bending moment, I told EI times square of second derivative of V with respect to X. It's not square. It's V second derivative of V with respect to X. Anyway, earlier it was by mistake. There is. Okay. So please take a note of this bending moment. And if you take one more derivative of this curvature, you are going to get this one, and up to multiply with the EI, you are going to get shear force. So please take a note of all these equations. Then we will see an example. So whatever explanation I gave you just before this slide, that is now you can recall. Displacement, this element is going to capture if the displacement variation is up to cubic, this element is able to capture exactly. Similarly, this element will be able to capture exactly the bending moment if the variation is linear, up to linear, and this element is going to be capturing exactly the shear force if the shear force variation is constant. So those things you need to keep in mind. When shear force is going to be constant, when bending moment is going to be linear. So only those cases this element is going to give you exact result for bending moment and shear force. If bending moment variation is quadratic, if it is a distributed load, let's say simply supported beam distributed load, bending moment is quadratic. So then this two node element is going to have some problem. It will not be able to give you exact value for bending moment. Similarly, for simply supported distributed load, shear force is not going to be constant. So this element is not going to give you exact result for shear force. Okay. So please take a note of these equations. Once you get the nodal values, once you get V1 theta 1, V2 theta 2, this is what is as a part of post processing. Finally, please you do whatever mathematics you want. Finally, I want to see what is bending moment diagram, what is shear force diagram. That is what structural engineers require, because based on that only we are going to design our reinforcement. So do whatever mathematics you want, you follow whatever conventions you want. Finally, you give me shear force diagram, bending moment diagram. To draw that, you need to do this interpolation over each element, and then over that element, how the bending moment is varying. Draw it as per the sign conventions. That is how the procedure goes. Okay. Similarly, shear force. Any questions? So if there are no questions, let's go to that simply or this continuous beam subjected to a concentrated load acting in the middle of mid span. Please take a note of this. Everything is given in SI units. 3-span continuous beam. And when this kind of problem is given, it is important to decide where the node should be. How many elements should I consider? Can I consider each span as one element? Or should I have a node at the point where the loads are applied, node at a point where concentrated moment is applied? All those things you need to be careful. Okay. So here this is a 3-span continuous beam. And just now we noted whatever 2-node beam element that we develop, that is going to capture up to quadratic bending moment exactly. Sorry, up to linear bending moment exactly. Up to constant shear exactly. Okay. So in this span, in the first span, if you see, there is no load. Okay, there is no load. So we can use one element in that span. And suppose instead of this 3 spans, let's say only 2 spans are there. It's simply supported beam subjected to a point load. You always need to have a node at the location where you are having concentrated loads or moments. That you need to keep in mind. So in the first span, one element is enough. In the second span, out of compulsion, since this is a point load, a node should be there in the middle. In the second span, you cannot have single element. You should have two elements. In the third span, only one element is enough. Okay? And if it is, as I just mentioned to you, instead of these two intermediate support, let's say I have a simply supported beam subjected to this point load at the middle. Then I need to have a node at the point where load is applied. So for that kind of situation, I need to have two elements. Okay? So for this problem, if you want to solve this entire problem, you need to have one element here, one element here, one element here, one element here. And a node should be there at this point. Node should be there right at the load point where load is applied. Otherwise, it's difficult for us to apply these force boundary conditions. So we should have one node here. Okay? And and once you have that kind of, that is what is called discretization. Discretization or domain or division of the given problem. Dividing the given problem into number of elements. So once you have that kind of discretization, you assemble element equation for this, each of these elements. This element, let's say this is node 1, 2, 3, 4, 5. And please note that if you want to solve this entire problem, there are going to be 5 nodes, 1, 2, 3, 4, 5 nodes. At each node, you have 2 degrees of freedom. So finally, the equation system is going to be 10 by 10 equation system. It doesn't matter. So first element is joining node 1 and 2. So making use of this equation, element equations, depending on its length, depending on its flexural rigidity, you get this assemble stiffness matrix. Depending on the loads applied, you assemble this one. Okay? So that is how you can get the element equations for element 1. Element equations for element 2. Element 2 is joining this node with a node here, right under the point load. And get the, for that length, here 400 is the span of this the distance between this support. I'm taking a middle point, so it's going to be 200. 200, based on 200 length, you taking flexural rigidity EI, you assemble the stiffness matrix, force vectors. Okay. Please note that this node is common to this element. If you decide to have one element here, one element here, this node is going to be common for both elements. And when you are assembling the force vector, you count this force only for one of the element. You cannot have duplication, okay? Because only 8 kilonewton load is applied. Otherwise, if you want to split equally, you consider this as 4 kilonewton to this element, 4 kilonewton to this element. It is up to you. Or you just put this 8 kilonewtons as a stiffness contribution of one of the element. Other element contribution is going to be 0. You can do that way. Or you can make it half, 4 kilonewton contribution to this element, 4 kilonewton contribution to this element. Finally, that contribution is going to go into the same node location. So finally, 8 is going to be there. Okay, think about it. And this element also you can assemble because there are no loads or anything. So once you get all the element equations, you can assemble the global equation system. And you get 10 by 10 equation system. Solve for the unknowns. What are the unknowns? Unknowns are this is all the supports are simply supported. Okay. So here this transverse displacement is going to be 0. 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 V1, V2, V3, V4 are going to be 0. Unknowns are going to be theta 1, theta 2, theta 3, theta 4. Rotations at each of these 4 points. They are going to be, sorry, rotations at here. I forgot that if you have a node here, this is going to be node. Let's say this is node 1, node 2. This is node 3, node 4, node 5. So thing is, just a minute. Let me step back. So V1, V2, V4, V5, they are going to be 0. V3 is not going to be 0. V3 is the displacement or transverse deflection at this point. And theta 1 is going to be, it's not going to be 0. Theta 2 is not going to be 0. Theta 3, based on your structural analysis concepts, you should be able to tell me whether theta 3 is going to be 0 or not. At this stage, if you don't know whether theta 3 is going to be 0 or not, or even if you know, you want to check whether finite element is going to give you that value or not, you can assume it is unknown, and theta 4 is not 0, theta 5 is not 0. So total 4 degrees of this V1, V2, V4, V5 are 0, and rest of the quantities, all thetas at all nodes can be calculated, and transverse displacement at the mid node can be calculated. Okay, so this is how you can do this problem if you want to solve this full problem. But usually in finite element method, first of all, whenever we say this kind of numerical methods, we look for efficiency of these methods and take advantage of reducing the equation system wherever possible. And this is a problem where there is a symmetry. This is a problem where there is a symmetry. Okay. So you can take advantage of that symmetry. So if I cut this beam, if I cut this continuous beam exactly in the middle, the way this portion is going to behave is going to be same as the way this portion is going to behave. So it's enough if I try to find what is going to be displacement or transverse displacement here, transverse displacement here, transverse rotation here, or rotation here, and transverse displacement and rotation at this point. It is enough if I find that exactly same thing, mirror image is going to be there on the other side. So in finite element method, wherever possible, we'll take advantage of that symmetry. Okay. So if you want to take advantage of symmetry, you should be careful. You should be careful when you are applying the boundary conditions, because a symmetric boundary condition need to be imposed on the plane of symmetry. If you are not sure about what symmetric boundary conditions you need to apply, then best thing is solve the entire problem without taking symmetry into account. Okay, but if you are good in identifying what exactly is going to happen on the plane of symmetry, then you can make use of symmetric this one. Take advantage of symmetry and reduce the size of the problem. So the point I want to make is this one. If you are not sure, I told you whether theta 3 is going to be, or the rotation right under the point low is going to be 0 or not. If you are not sure, don't take risk. You solve the entire problem. Let the solution whatever solution you get, let it show whether it's going to be 0 or not. But if you are really sure about symmetry and you are clear about what the behavior is going to be, then you can go ahead and do the symmetric model. Symmetric model, half of it. So you assemble one element here, one element here, but you should be careful. You should be careful about this imposing the boundary conditions. And also how you are splitting. When you take symmetry, this 8 kilonewton go into this as 4, this into 4. So that also is split. And the symmetry boundary condition. What is the symmetric boundary condition? There is going to be vertical displacement or transverse displacement, but rotation is going to be 0. So if you are not sure, if your structural analysis background is weak, if you are not sure about it, you better don't take this risk. You solve the entire problem. Otherwise, if you are very clear about it, then you take this one, reduced problem. Reduced problem has only 3 nodes, 1, 2, 3. The nodes are numbered here 1, 2, 3, and element 1 is connecting node 1 to 2. Element 2 is connecting 2 to 3. Element 1 length is 400 mm. Element 2 length is 200 mm. All the element equations are assembled, and there are no loads except one load here, which is a concentrated force acting in the downward direction, which is in the negative direction. So taking note of all that, element equation for 1, element equation for 2, second element, they are assembled. Element equation from 1 goes into the global. If you take these 2 elements, taking symmetry into account, you are going to get 6 by 6 matrix because 3 nodes. Element 1 contribution goes into 1, 2, 3, 4 rows and columns. Element 2 contribution goes into 3, 4, 5, 6 rows and columns. And get the element equations, apply the essential boundary conditions, and then solve for the unknowns. So we'll continue in tomorrow's class. Wherever we left in today's class, we'll recap all that. Okay? Thank you. Just a minute. Let me take attendance. Okay, thank you.
Sir, sir, what's the syllabus for quiz 1?
Huh?
So syllabus for quiz 1.
Not understanding.
So I'm saying, what's the syllabus for quiz 1?
Both the? I'm not understanding your question.
Sir, he is asking the syllabus for quiz 1.
Quiz 1, everything I told you, all the whatever is covered. I gave you 4 assignments in the fourth assignment up to 10th problem, whatever portion that is covered, that is all going to be there for quiz. Till whatever we covered till last Friday, it is there for quiz. Okay? Any questions?
Sir,